Suppose we want to find the center of mass of a system of particles. Okay, so for example, say our system consists of two parts, one with a mass m1 and the other with a mass m2. Now we want to locate the center of mass relative to an origin. So I'll say that this is the origin. Okay, mass 1 is located at a position x1 from the origin. Mass 2 is located at a position x2 from the origin. To find the center of mass, xcm, we take mass 1's position, x1, multiply it by the value of mass 1, which is m1, add that to the position of mass 2, multiply by the value of the mass of mass 2, m2, and divide that by the total mass of the system. Okay, that will give you the location of the center of mass with respect to the origin. Cm. Now suppose that m1 and m2 are moving. Doesn't matter whether m1 is moving to the right or m2 is moving to the left, or they're both moving to the right or they're both moving to the left. They're both undergoing a displacement. So what we're going to do is determine the displacement of the center of mass. So we just put deltas in front of the x1, the x2, and in front of xcm. And this is the expression for the displacement of the center of mass. Now, of course, this occurs over a time interval, delta t. And if we allow the time interval to shrink to 0, then what we have here is the instantaneous velocity of the system's center of mass. Divide by t on this side, and what we have here is the instantaneous velocity of mass 1 and the instantaneous velocity of mass 2. So our equation then for the instantaneous velocity of the center of mass is VCM is equal to V1 M1 plus V2 M2 divided by the mass of the system. Okay, so this equation and this equation are handy equations when working with center of mass. Now, as long as there are no net external impulses, the center of mass will keep on doing what it's doing, either at rest or traveling at a constant velocity. Okay, here we have a track that's balanced right here, and I have two carts of unequal mass on top of the track. Okay, the center of mass of these two carts lies directly over the pivot point here that this track is balanced on. Now what I'm going to do is I'm going to allow this. Okay, what I have here are two carts of unequal mass that are on a track that's balanced on the fulcrum here. The center mass of the two-cart system lies right over the fulcrum. There's a spring-loaded bumper in here, and when I allow the spring-loaded bumper to expand, it's going to exert a force on this cart from Newton's third law, force back on this cart. Because those forces are internal, there will be no acceleration resulting for the system. So the center of mass's acceleration should remain 0. Another way of explaining this is that there are no net external forces acting on the system, so the center of mass should remain at rest. It should remain with. Okay, what I have here are two carts of unequal masses, and they're on a track that's balanced on fulcrum. And there's a spring-loaded bumper between the two carts, and I'm going to release that, and that spring-loaded bumper, as it expands, is going to exert an impulse on this cart and an equal but oppositely directed impulse on this cart from Newton's third law. But since they're internal impulses, the momentum of the system will not change. Therefore, the center of mass of the system will remain at rest. So the track should remain balanced. Okay, so let's give it a try. Suppose there is, though, an external impulse. If there is an external impulse, according to Newton's second law of motion, the net external impulse will cause the system to undergo a change in momentum. But that will be the change in momentum of the center of mass of the system. Now imagine I take this system with the two carts, with the spring-loaded bumper between them. Okay, now you know where the center of mass is there, approximately. And I take this whole system and I drop it. Well, again, this track should remain horizontal, and the center of mass should just continue moving downward under the influence of the net external impulse. And it should result in a constant acceleration of 9.8 meters per second squared. If I threw the track and somewhere along its trajectory, the center of mass's trajectory, which is a parabolic curve, I release the spring-loaded bumper, the carts will move away from each other, of course, but the center of mass will still follow the parabolic path. Turns out that center of mass will always follow the simplest path when under the influence of a net external impulse. Here is an irregularly shaped object whose center of mass is right where I have the flashlight mounted. You can see that I can balance it there. Now if I toss this through the air, put it into free fall, the center of mass of the system will experience a net external impulse. Okay, and that is caused by gravity, of course, so that should cause the center of mass to accelerate downward and only downward at 9.8 meters per second squared. And the center of mass will follow a nice smooth parabolic curve. Now to demonstrate this, I will turn out the lights in a moment, and you'll see the light traced across the room here following a nice smooth parabolic path. Then what I'm going to do is I'm going to place the flashlight away from the center of mass, and I'll toss it. And this time you'll see the light follow a very complicated path, because it's only the center of mass that follows the simplest path, which would be a parabolic path in this case. The center of mass of the system, in the case of, let's say, a stick of dynamite that you throw through the air and explodes, the center of mass of the system will continue to accelerate at 9.8 meters per second squared. And all the pieces will land on the ground, and the center of mass of all those pieces will be located at the very spot that stick of dynamite would have landed if the stick of dynamite did not explode in the air. As another illustration, consider a ballerina who's jumping through the air, and the ballerina jumps through the air and doesn't change the shape of her body. Every part of her body will follow a parabolic path. Okay, the center of mass will, and every other part of her body will. If as she goes through the air, she doesn't change the orientation of any part of her body. However, as she goes through the air, if she does something like this, Okay, what that will do is raise her center of mass relative to other parts of her body. But her center of mass must still follow the parabolic curve that it originally followed, right? Because the only net external impulse on the ballerina's body is still the force of gravity times time. So the only external force on the ballerina is still her weight. So that her center of mass must still behave like it did before. So as a result, other parts of her body adjust, keeping her center of mass on that parabolic path. So there's a particular routine that ballerinas do where their head appears to travel horizontally across the stage, while the center of mass of her body still follows the parabolic curve. Another illustration. Okay, let's take a look at a video I made and analyzed of a ballerina jumping through the air. Another illustration deals with the Earth-Moon system going around the sun. Okay, so suppose this is our sun. Okay, here's the orbit of the Earth-Moon system. Now that's actually the orbit of the center of mass of the Earth-Moon system. It turns out that the center of mass of the Earth-Moon system actually lies a little bit below the surface of the Earth. So it's the center of mass that goes around a nearly circular orbit. But the moon goes around the Earth, and the Earth actually goes around its own center of mass. Okay, the center of mass of the Earth-Moon system. So the path taken by the moon looks something like this. And the path taken by the Earth looks something like this. So we have these two sinusoidal curves.